you know, there is a change of program, and I am very glad to introduce a colleague from the physics department of college that, as far as I know, it's the first time that speaks in Untitled Algebra conference, so it's very welcome. And also, I'm introducing Benjamin Doyon, and that he will speak on conformal field theory out of equilibrium.
Yeah, thank you, Roberto. So yes, a pleasure to be in this conference on operator algebra. So thank you for the invitation. So I have to say I'm a little bit of an outsider here. I'm really a physicist, not a mathematician, although I am in the department of mathematics. But this is a special, special properties of the UK that you have a lot of physicists in mathematics department. I'm in the theoretical physics group, and my background really is on quantum field theory, and especially integrable quantum field theory. This is my background. I've done a lot of research in that area. I've done actually a lot of research in application of quantum field theory and conformal field theory to statistical mechanics problems and to quantum physics and all that. Okay, and so the talk that I'm going to be giving today is very different from the other talks that we've heard in the conference. And actually, I'm very happy to be in this conference. I'm learning a lot about operator algebra, but this is not really about operator algebra. So I apologize for that. It's about application of conformal field theory to problems which are really, quite high profile nowadays in physics. And I think what's interesting is that what I try to point out the various open problems that they are, which are interesting from the point of view of operator algebra, from the point of view in particular of obtaining rigorous proof or rigorous understanding of certain physical phenomena, which are really of high interest nowadays. Okay, so this is a bit kind of the goal of this talk. But it's a physics talk, so I am asking you to put your physics brain a little bit, and so let me start. Okay, if I may ask.
Physics start.
Huh?
Physics has start.
It's a sorry.
It looks like physics has started here.
Yes, exactly. This is very much physics style, isn't it? Yeah. So I start with that. So this is a physics problem, right? Extremely simple. So the physics problem that we're looking into is the following. So we want to study. So in statistical mechanics, people have spent a lot of time in the past studying equilibrium properties of statistical system, either quantum or classical system. This is very much understood. There's thermodynamics. There's a lot of it. There's even a lot of nice rigorous results. And nowadays, actually, there's a lot of emphasis on developing theories for systems which are out of equilibrium, so non-equilibrium systems. So this is not described by games and symbols and all that. Okay, I mean, this has started from quite some time ago, but nowadays there's a lot of emphasis on that. And one of the particular type of states that people are looking at, which are relatively simple, so that you can perhaps understand them quite well, but yet out of equilibrium, are the steady states, non-equilibrium steady states. So what are these? These are states where you have flows of energy or particles or something between two baths. Say. The flows are constant, but there's a flow, so it's not equilibrium. So there's a change of entropy, if you wish. In physics, the entropy increases, there's a flow. Okay. There are various ways of creating these steady states. One of them is called the partitioning approach, and it stands within a much wider context of non-equilibrium dynamics. It's been studied for quite some time, and it goes as follows. So you imagine now you have two quantum systems, very, very large, separate, okay, and you thermalize them. So you put them in Gibbs states or KMS states at different temperatures or different equilibrium states, different configurations. And then suddenly so this is the initial condition, suddenly you connect them on some interface. So we can imagine two half chains and connect them at one side, two half line, connect them to make a full line. Okay? So physically what you would expect is that energy, suppose this one is hotter than that one, will start flowing from left to right. It will be energy flowing from to right. And eventually, in the very large time limit, if we look in the right regions, in the central region, we should see something that is steady, and perhaps we'll see a steady current of energy. And that will be the steady state. And so the point of this problem is to try to describe what that steady state is. Okay? So the steady state, the state that occurs after a very large time of evolution in an even larger system when you look in some finite region. Okay? That's the state. And so actually, I've given this talk many times in different situations. I always ask the audience the question, what do you think will happen? So if I take arbitrary system, just some quantum many-body systems like that, and I do this operation, and I wait a long time, and I look here, what will I see there from physics? What should I see? Should there be a current? What kind of state should that be? So if you take two bars of metal of different temperature, you connect them, let the whole thing evolve, what do you see after a large time?
What would be different between the quantum and classical?
Well, that's also a good question. So here, there's no difference from my question. There's no difference, quantum and classical. Okay, that would be generally. Okay, actually, in this time from, there is not a lot of difference between quantum and classical. And the formalism is different and all that. But some of these papers I cite are classical, some are quantum, and it's the same type of idea. Okay, so no, not too many differences. Okay, so what will happen? So what will happen? You know, physics-wise, what we expect if you let the system evolve arbitrarily, it just goes to the most natural state it can go to, which is a thermal state, a Gibbs state. Okay?
So there would be actually an equilibrium state?
Yes, so it will be an equilibrium state.
Uh-huh.
So in generic systems, we would expect that to be an equilibrium state. Okay? So this is not super interesting for, from that point of view, but we're not interested in generic systems. These people neither are interested in generic systems. There's particular systems where there will be non-equilibrium steady states, and these are particular non-equilibrium steady states that we can understand a bit better. So let me give you, I'll come back to what kind of system exactly there will be non-equilibrium steady state. Okay? So just keep in mind that generically there shouldn't be, but there are certain systems where there will be. I mean, some of them, for instance, are conformal field theory, and there will be something. Okay? And I explain why. So let me put a bit more of equations to that, just that we have the notation precise in our mind. And this is really just quantum mechanics. Okay, this is a.
Yes? I just want to understand.
Yeah.
If you have this like temperature as a function of position.
Yes.
Presumably, the steady state you're looking at is a linear function. So you need to have infinite temperature on one side and minus infinite temperature on the other side in order to have a hope for C.
Okay, so this is a very interesting question. Maybe I should go forward a few slides when I have the answer to that question. Well, okay, maybe I can tell you already. So what's happening? So I'm thinking finite temperature differences. Okay, your intuition is correct. From there to there will be a gradient of temperature. But if the temperature is finite there and there, and you imagine that because of there's some kind of diffusion effect, right? The gradient will be very, very small. Eventually, the gradient will be zero in the large time limit. And okay, if there's zero gradient, according to Fourier's law, which is a law for temperature current with respect to gradient of temperature, there should be no temperature current or no energy current. And indeed, that's in generic system. But in some systems, this is not the case. And in CFT, this is not the case. And there's a reason why. I'll come to that. Okay? Okay. So yes, just to set up the notation here, and actually this is a very interesting example of the Heisenberg quantum chain, where you can do this thing, where people have done this thing numerically and have analyzed what's happening. Okay? And our results, we have results in CFT, and these results actually have been proven rigorously by Holland and Roberto Longo. So our results apply to this case, for instance. Okay? Well, so this is an interesting example. So what is the example where you have a Hilbert space, say, of 2L sites. Some sites are on the left, so some sites on the right. And the Hamiltonian is a sum of local, on each site you have a spin half representation of SU2. So you have a C2 on each site. Okay? And on each site you can imagine Pauli matrices acting on these sites. Okay? So we can write down, so this sigma n is a Pauli matrix acting on site n is identity on every other site. Okay, that's what sigma n is. Okay? And the Hamiltonian is composed of a sum of such operators, and these operators act on neighboring sites. So this is called a local Hamiltonian. It's a sum of Hamiltonian density. That means the energy is measured by summing local energies on various sites. Okay? So the exact form is like that, sigma dot sigma. So you have a vector of Pauli matrices, you dot it. Okay? You have so Pauli matrices on neighborhood sites. And you can divide Hamiltonian into a left part, a right part, and the thing that connects the two parts, right? So you have a lot of sides. Hamiltonian always involves two sides at a time, And there's a left, there's a right, and then there's a part where these two sides connect the left and the right. So this is h left, h right, and the delta h. Okay. Is that clear? This just question. You look at me a bit.
I'm just thinking that with spins, you can have things which behave differently than you were trying to deceive us in the beginning. That's not just thermalization. Something else could go on when you connect to Heisenberg's.
Yes, yes. So I'm deceiving you a little bit, actually. So Heisenberg is very particular, actually. So this quantum chain is very particular. It's not a generic one like the one I was asking. Take a generic system. This is not the generic one. Okay. And that one will have a current because it's very particular. So yes, so of course this is a very particular. But you could imagine something more complicated, but this is good for the example for now. Okay? So we do that. Okay? And then what we do, the time evolution with respect to this full Hamiltonian of a certain state, omega 0, which is just a state where you have thermalized the left and the right, with respect to left and right Hamiltonians, without putting the connection between the two things. Yeah? So h left and h right commute with each other, it's independent, you have two separate systems, you thermalize the two separate systems. So that's initial state, but you evolve with the full Hamiltonian, the one that has a connection between the two things. So that makes energy flowing, and then that's the situation. Okay? And the question is, well, if you take now this thing and take the large L limit, you want to have a large volume, because if you want to have eventually some steady flow, you've got to have an infinite bath somehow that can carry a lot of energy. So large volume, and then after taking this large volume, large L limit, you take a large time limit. The question is, does that limit exist, and does it carry a current? Does it carry a state? So that's the main question. So is it stationary? If it exists, it should be stationary, so it should be invariant under this evolution, the
Of course,
time derivative.
the limits do not commute, of course.
Do not commute. The limits do not commute. It's very important. If I were to try to take L finite and large T limit first, what will happen? Well, since it's finite, kind of energy would kind of go back and forth, if you wish. I will have recurrence. Okay? No steady state. What people do sometimes is not take L finite, take large T, but take an integration over time. So integration over a large period of time and average over a large period of time. That's another way of describing a steady state, actually. And there the limit will exist, but it's slightly different. That's not what that one. This is the more interesting one. This is one. Okay. So that's what we would like to do. Okay. And so one thing what we could calculate is the energy current. What is the energy current? Well, it's the thing that occurs in the conservation equation for the energy density. So Hn is my energy density, right? It's the product of these Pauli matrices. If I take its small time derivative, right, this delta H is notation for this commutator with Hamiltonian, that's the time derivative. Okay. This is still a local, something supported on finite number of sites, and that satisfies this equation. So there's a Jn plus 1 minus Jn, which is like a gradient, but in finite, on spin chain. And that Jn is this, and this is the energy current. Okay. And we'd like to know, is this non-zero or not? And if this is non-zero, we'll say, well, there's an energy current, so this is a non-equilibrium steady state. Okay. Not only is this not zero, but what is the value of that thing, right? So that's the holy grail, right? Calculate that number, okay, in this limit. And it has recently been calculated, not rigorously, but from physical arguments based on hydrodynamics. And it's not just a number you can write. It's a solution of some complicated integral equations you have to do numerically. There's some conjectures for that in that model. Okay, so questions about this.
Do you expect a unique limit always?
Well, so this is well-defined, system well-defined. So there's if the limit exists, there's a number there.
Oh, but could be several weak limit points.
Yes, there could be several weak limit points. So this I don't know. Okay, so here you see. Here I'm thinking this is quite non-trivial in what sense the limit exists actually. So here I'm taking really the weakest sense by looking at these operators O, which are on finite sites, like this current there. So product of Pauli matrices on a finite number of sites. Okay? That makes sense. Okay? But you could look at other type of operators. That might be a different limit. Okay? And in fact, depending which O you have, the limit, the way you describe the limit may well depend on what family of operators you look at. So this is a non-trivial question as well, which operator you want to look at and how you describe the state. Okay? So for now we have a physical understanding for a certain family of operators which are conserved densities and currents, but not for everything. Okay? So just for a certain family of operators. Okay, yeah. uniqueness of the limit. Yeah. Other questions? Okay, so there's a lot of open questions here. So there's absolutely no rigorous result for that for that model. Okay.
Current, just a small comment
Yeah.
or half question. The current is
Yeah.
3 locals, so to say, right? It takes 3
Yes.
adjacent sides.
Mhm.
Is there a good intuition for that?
Well, the basic one is that the energy density is too local,
Yeah.
and then when you take
Yeah.
derivative, you add a.
There has to be something like yeah.
But otherwise, no. I mean, there's no. There are, in other models, it might be on more sites than 3, depending on the. That would be model dependent. That would be model dependent. The important thing, I should say, is that the current is a parity odd. Is parity odd, okay?
Because of the product.
Yeah, because of this product there. While the Hamiltonian, of course, is parity even now. That so if you had a thermal state, of course, it would be parity even. So any parity odd operator would have 0 average if you have just a thermal state. So this is the fact that it's non-zero is quite special for a system evolved with a parity even Hamiltonian. It's quite special. That's one characteristic of the fact.
What's the definition of the cross, as a matter of fact?
So this is this is a physics notation. So this is the usual vector product
Of two-dimensional.
these are 3 vectors. There are 3 polymetrics: sigma x, sigma y, sigma z.
Yes.
And so this is sigma y, sigma z, sigma y, vector product. Yeah. Okay. So yeah. So for generic quantum chains lattices, the whole thing is expected to be trivial, no thermal flow. That is, this should be 0. Okay. So as I said, by parity. And that's based on the Fourier law, as it was comment. Indeed, who would expect 0 gradients or 0 Fourier law. So a generic one. Okay, that's physical expectation. Let's go a bit more for. So I have a comment. So if you want a non-conformal steady state, there should be something called ballistic transport, because Fourier's law is what people call diffusive transport. It's a particular type of transport. It's diffusive, so it satisfies certain laws. So we should have a different type of transport, which is ballistic. So ballistic is, okay, when you throw a ball, for instance, you start throwing it and it continues forever. Well, this is it. There should be something like that. You start throwing the particle because of the difference of energy, and it should continue forever, right? Okay, so what do we expect more precisely physically? So why do we say it should thermalize? Well, the basic intuition is that the entropy should be maximized. That's what we usually say. In physics, you have a many-body system, you get somewhere, so entropy should be maximized, okay? So if entropy is maximized, that means that the density matrix, there's no actually density matrix formally for the stationary state because it's infinite volume. But in physics, we still think about density matrix. And we say, well, it should be of the form of the Gibbs density matrix, an exponential with something in the exponential. And the thing in the exponential should involve all the conservation laws that are conserve under the dynamics and that don't thermalize. Okay? So all the local conservation laws. So for instance, the Hamiltonian is conserved under dynamics because it commutes with itself. So you can have the Hamiltonian there. But if you have other conservation laws, then you can put them there as well. And the maximal entropy principle will tell you, well, you maximize entropy under the condition of these conservation laws. So you should get to the density matrix of that type. You have a question?
Just the road to integrable generalization of the whole thing.
Yes, exactly. So you see, the usual thing is exponential minus beta h that gives, and that's entropy maximization. But the generalization is, well, actually you can put any local conserved charges there. The local conserved charges are those that are of the type sum over n of some local density supported on finite number of sites around the site n. Local charge. One can give a very precise definition for what these are. Okay, local conserved charge. And so, if you have an integrable system where there are infinitely many, then you can have something very different from Gibbs. Okay? Or if you have any system where you have for something else Hamiltonian, you have something different. And so you will have a ballistic transport if there exists among these conserved charges one that has appropriate antisymmetry property, one that is parity odd, because then it could support a current, non-zero average current. Okay? Maybe not, but it could. Okay? So this is kind of a condition, tantamount to this condition. That's what we're looking for. Okay? So what kind of system that will be the case? Well, as we said, integrable systems like the Heisenberg chain is integrable. That's why it carries a current. It has such conserved charges. Okay? So the stationary state can be expressed in that way. But also other systems which are more generic than integrable systems which are any systems that are near or at quantum criticality, because such systems are described by quantum field theory or conformal field theory. And in field theory, there is continuous translation invariance, so there's a momentum operator P, which is parity odd. And so stationary state may have this form, beta H nu P. Okay? And depending on what the value of beta and nu are, we may have a non-zero current. And so the problem is calculate beta and nu in terms of liethe, right, in a QFT or in a CFT in that setup. Okay? So you would expect stationary state to be describable in that way. So the more precise version of that would be, since this you have taken the infinite volume limit now, that would be that the stationary should be KMS with respect to a certain evolution, which is a linear combination of H and P. Any questions about this? So that's the physics, right? That's what we expect physically. Okay? In particular, in integrable models, well, integrable models, of course, it would be much more complicated because you may have infinity of them, of these conserved charges. And these are called generalized Gibbs ensembles. They've been studied a lot recently. And yeah, so all this stuff, I should say, there's still a lot of open door for rigorous studies, particularly in integrable systems. Okay? But also in QFT and CFT. Okay, so any questions about this?
I don't quite see how you tell when it's going to be KMS and when not.
What do you mean?
Well, you said that sometimes it is and sometimes it isn't.
Well, so all I'm saying is, you see, this is physical intuition. I write these density matrices, okay, like Gibbs density matrix. I would expect a stationary state to look like that. Okay? So I would expect it to look like that. But I know that this is an infinite system, right? So Hamiltonian momentum not quite well-defined operators. And so if I reinterpret that formula, I want to write it correctly formally for that state, I would say, well, what I would expect is to have a KMS state with respect to that evolution. Okay? That's kind of the physics argument lead to that statement which can be made precise mathematically and can be checked or proven or stuff like that. Okay? See, the idea with that is you have a system, okay, then you think of it physically, you get to some conclusions. Now that you have to rewrite your conclusion in a way that makes mathematical sense and then prove, right? That's the point of it. Okay? So the question: is it true that in that system, in that setup, the stationary state is KMS with respect to that and that? Okay. Other questions? So let me then discuss conformal field theory. So this is a situation where we have a momentum, so we should expect to have such thing. In conformal field theory, one can do calculation very precisely. In fact, it's a rather simple calculation. So I'm going to do the calculation for you. This is a physics notation. Of course, that's the way we did the calculation originally with Denis, okay? And where we could calculate exactly where the current was and what the stationary state looked like and how it is. Okay? So what is that? So we take the point of view of local fields, right? Remember that we have operators on finite number of sites. When you go to the CFT, these are fields that depend on the position x, and x here is on R. Okay? In CFT, there is a particular field which always is there, okay? According to the physical principle, which is called the stress energy tensor. This is just something that combines together the energy density and the momentum density and their current. Okay? And the stress energy tensor, so it's a 2x2 matrix, if you wish, and it satisfies certain properties in CFT. One of them is that it is symmetric because of Lorentz invariance. That means that the energy current is equal to the momentum density. That's a physical equation. The other is traceless, and that's because of scale invariant. So when you take a scaling limit, you have scale invariance, and that means that the momentum current, which is the pressure, is equal to the energy density. Okay? So overall, it's a 2x2 matrix, which is symmetric and which have a very simple form, right? It just contains the two non-trivial quantities that we have, which is the energy density and the momentum density. And these are the densities for the energy, Hamiltonian, and the momentum operator, right? So this is the continuous version of what I was writing on the quantum chain, right? So that's kind of the initial given data of conformal field theory from physics perspective, right? And the stress energy tensor, it satisfies conservation equation. So basically, the Hamiltonian and the momentum are conserved quantity are invariant under time evolution, and that implies that their densities satisfy conservation laws, local conservation laws. And these local conservation laws, they are just the statement that d mu t mu nu equals 0. The stress energy tensor is a conserved current, is two conserved currents. Okay. So that means that we can construct, so because of this very simple structure, then we can just construct linear combination of h and p, which I call t and t bar, which satisfy very simple relations. So t satisfies dt plus dx equals 0, and t bar dt minus dx equals 0. And as a consequence, that particular operator, is t, which is energy density plus momentum density, when you time evolve it, with this tau t, it just becomes the same operator but at x minus the time. Right? So it evolves in a trivial fashion. T bar evolves in a trivial fashion but in the opposite direction. Okay? So this is chirality. That means that in CFT, whatever conformal field theory you have, so when you take a scaling limit of a quantum chain, you always have particular operators that represent energy density and momentum density, which evolve in a very, very simple fashion under the full quantum dynamics. Okay? Now this is a few lines to describe something that's very basic in CFT, but it is actually extremely non-trivial, because if you take your quantum chain and evolve the Hamiltonian density Hn, it's something very complicated. Right? It's a complicated operator. But we see that when you take a scaling limit, which is really low energy limit, large distances, it can be completely described by this simple time evolution. Right? X minus t, x plus t. Okay, that's the basic. And so actually with that, one can already give the value of the current. It's very simple. So you imagine that you have here left temperature, we call it beta left for inverse temperature, and beta right there. Okay. And you want to know the value of the momentum p, which is t minus t bar. I might have mixed some factor of 2 there, t minus t bar. Okay. At some point 0. So you want to know this value, t minus t bar. Okay? So the average after a very large time from this initial state. Okay? So you know that t is a right mover. Okay? That means that it moves, so its evolution gets its x minus t, so it moves towards the right. Okay? So t, if I want to know this value there, I'm going to have to look towards the left, because it comes from there. While t bar, so this is t bar, if I want to know its value there, I'm going to have to look towards the right, because it's a left mover. And then, so that's t bar. And so the average of t at this time is equal to the average of t at 0 time in that initial bat on the left. This is very simple, right? So from this I would say omega stationary of t minus t bar is simply equal to the Gibbs state value, omega beta left of t minus omega beta right of t bar. And these values are known in CFT. This is standard conformal field theory. So that can be written exactly as the central charge of CFT, c pi over 12 times beta left to the minus 2 minus beta right to the minus 2. Okay. And this is indeed non-zero if the two temperatures are different. So there we have the exact calculation of a non-program current in CFT. Just using that. So this is just really, really a simple argument. Okay? Now, I'm skipping a lot of things there because these initial conditions are on the half line, it's not on the full line, right? So these initial values are on the half line, so you have to be a bit careful. So if you want to be a bit more careful, and if you want to describe the full stationary state, not just this average value, you have to do a bit more work. Okay? So let me describe a little bit more what we can do kind of more precisely to get the full stationary state and the bigger picture. But do you have any question about that now? So yeah, okay. So in CFT, we have more than just the stress energy tensor, of course. There are many other fields, many other observables, and it's interesting to look at them. And one way to generate observables is via the Wilson's operator product expansion, which says that if you take product of two local fields, you can always expand that in differences of their distances, of their position in the distance. And what you get as coefficient of the expansion are other local fields. Right? And these are local fields that occur in the algebra of these other local fields. So this basically forms an algebra determined by the structure constant. In fact, the formal way of describing all this is via vertex operator algebra, where you have really an infinity of products corresponding to all of these, this is sum over k, to all of these elements in the series. Okay? So you have a lot of fields that you can construct that way. So if you put stress energy tensor here and there, or you look at all the things that appear there, these are a lot of fields. Okay? So these are fields, and you can understand these fields as forming a vector space. It's an infinite dimensional vector space, and the whole CFT then is basically a vector bundle. We have the vector space tensor R being a space on which you have the stuff. So at every point you have this whole vector space. Okay? So these local fields can be seen as sections, and P is like a transport, parallel transport on that fiber, on that vector bundle. Okay? So you have a big vector space that contains the stress energy tensor component. Okay? Now, by the fact of chirality, so T being right mover, T bar left movers, there's a lot of consequences that come out from that. Okay? So in particular, if you look at how the field generated by T, so you put T there, and look at everything there and continue generating all the fields, all these fields, because the time evolution is a automorphism of this algebra, all these fields will be right movers. So you have a whole algebra of right moving fields, not just a stress tensor, and a whole algebra of left moving fields. Okay? And these two algebras kind of trivially factorize, and so really the whole sector generated by the stress tensor is a trivial, it's kind of a tensor product of algebra generated by T and T bar. So it's like V plus times V minus. Okay? So there's a whole algebra, these things that contain the stress energy tensor. Now, the word identities, so there are other constraints that come from quantum field theory. Some of them called word identities, other physically motivated constraints. They tell you that actually if you look at the OPE of TT, some of the terms are completely fixed, like that. There's a constant there. There's a constant in particular well, the fact that these terms are fixed means that these V plus and V minus contain the Virasoro algebra, and so these are the Virasoro vertex operator algebra. Okay, so this is the algebra of these local fields, and Virasoro algebra has a set of central charge C, which is related to that number. A is not exactly the same, but related to that. Okay, so that's the situation. So we have two Virasoro vertex operator algebras, not just stress tensor. Okay, so V plus and V minus, two copies of that. And then we look at states. So the states are average of operators at different points. Okay, many points and average of these operators. So you can think of that as a product of these sections, and they also, all of these products have the structure of tensor product V plus times V minus. Okay, so you can always separate the whole algebra into the right moving and left moving thing. These average, so in physics we look at average of local operators. So these are functional on product of fields given complex numbers. We always should take the position to be different, because otherwise the result is infinity. So it's not quite a state from the point of view of operator algebra. That's because we're concentrating on local fields, and that creates a lot of problems. Okay, but that's fine for the calculation. So now we want to describe these states. So I have to consider states there. So let me describe these states. So if I want to construct a give state on the line, well, the chirality, the fact that stress tensor are right moving and left moving, already tells me a lot. Okay, so because so any state that clusters at large distances will have to factorize on these two algebra. Okay, that's because if I take a state which is a product, state evaluated on the product of T and T bar, and if I should say not any state, any stationary state. So if the state is stationary, then I can time evolve the whole thing. As I time evolve, all the right movers goes on one side, the left mover on the other side, so they separate a lot. And if the state is clustering, then it will be a product of these of the values on these two groups of operators. Okay, so this will always have to look like a factor which contains all the t's and a factor which contains all the t bar. Okay, so the state overall gives state on that algebra of fields, okay, can always be written as a tensor product, or a product of states that act, one on the right movers, the other on the left movers. And these two states are give states, or KMS state, with respect to a particular evolution. One is a right moving evolution, the other is left moving evolution, H plus minus, on these subalgebras, on these factors of the algebra. Okay, so that's an important notion here, that the give state in the energy sector factorizes into give state on two different algebras, one for right moving fields, the other for left moving fields. Okay? So that's really as a consequence of chirality. Okay? So here I introduce the H plus minus. This is combination of Hamiltonian momentum, and it acts so it acts trivially on the, so H plus will act trivially on H minus and vice versa. Okay. So yeah, okay. Any question about this? Okay. So we have algebra of fields, right mover and left movers, and we have state that factorize on that. Now what we need to describe here are not just the state on the full line, but the initial states, which was on the half line, right? So I had half chain on the left and half chain on the right, which I then connected. Okay? So on the half line, it turns out that one can use, represent the state on the half line by using states on the full line, and by using a particular isomorphism of algebra. Okay? Turns out that if you take t bar of x to t of minus x, the OPEs between the t bars are unchanged. Okay? So this is a symmetry of the operator product expansion of Wilson's OPE symmetry. Okay? And you can use that symmetry then to represent a state on the half line. So the half line, the important bit is that there is a restriction. So if you look on the half line, say from minus infinity to 0, at the point 0, you don't have two copies of vertex operator algebra, but you just have a single copy. So at every point you have this fiber, this vector space where you have two copies of vertex operator algebra, and at the point 0 you have a single copy. Okay, that's basically the idea, and that's the Carlius boundary condition. Okay? And so that means that this space of field should be the space of field on the half line without 0, and then a single copy of the vertex operator algebra as 0. Okay? And state on this space, so any KMS state on that space and time evolution on that space can be represented using a particular unfolding isomorphism. This unfolding isomorphism, what it does is that it takes the t's which are on the left and map it to the t's on the left, but the t bar on the left map it to the t on the right. So this physically is extremely simple. I write it here. So you have your half line where you have right movers and left movers. The boundary condition says that t equals t bar, so you kind of connect these two things. So you're left with a kind of a single line, and the unfolding isomorphisms, it takes these left movers and unfolds it there to the full line, and so you're left with a full line, but with a single copy of the vertex operator algebra. Okay, so that's the basic idea. So at the level of algebras, it all makes sense. Okay, so this is what I call this kappa L that makes this unfolding, and so you can represent a give state on the left by composing a give state on the right movers only. This thing that factorizes, composed with this kappa L, with this unfolding. Okay? And similarly, the evolution on that, with respect to the H left Hamiltonian, is the evolution with the H plus Hamiltonian, so just the right movers, composed with this kappa L. Okay? So you can do that. Okay? Likewise, something for the right. So for the right, you would unfold by taking the right movers to left movers on the left. Okay? So you have these two unfolding isomorphisms. And that's how you describe the states on the half line. Okay? So with this, so states on the half line described in terms of states on the full line, but for single chirality, and states on the full line being the product of these two chiralities. With this, then we can easily, a few lines, it's just too many symbols here, but a few lines derive what the stationary state is, the full state. Not just the value of the current, as I did, the full state exactly. Okay, and on that algebra of fields, okay, within the energy sector. So what is it? Well, the stationary state is a large time limit of composition of tau t, so evolution with h, and the initial state, which is a tensor product of left and right at different temperatures, beta left, beta right. Okay. Now I can always compose in between these two things. With tau minus t h left times tau minus t h right, because that leaves the initial state invariant. So this omega left beta left is invariant on the tau th left, is stationary. So I can put that without changing anything. And then I concentrate on this composition of evolution. Okay? And this composition of evolution at very large time is what could be understood as a scattering operator on the set of fields. Right? It's like evolve with H and evolve backward with H without interaction. Right? It's something that's very standard in quantum field theory, actually. Okay? So we want to look at the large time evolution of that thing that gives you the scattering operator. Okay? Well, the large time evolution of that thing is not too complicated, because if you look at fields which are, okay, some fields which are right movers, some which are left movers, A plus minus, and do the H plus evolution of the right movers, well, that will always end up on the left. This is like this picture there. So the right movers come from the left, okay? Because the right movers get affected, X becomes X minus T, okay? For any large enough time. Okay? Of course, if time is not very large, then it might not end up on the left. It depends where the right mover starts with. If it starts very much on the right, then it will not. But at very, very large time, then eventually will end up on the left. Okay? And likewise, for the left movers will end up on the right. Okay? So that means that I can, in this expression, decompose my tau th into its chiral component of right and left movers, and compose them with this factor that acts on the left and on the right separately. Okay, so that's the idea. So if this time is large enough, this is always in the right space, so that I can put it there. Okay, so the time evolution with H separated into H plus H minus, I can put them there. Now that I have that, I can just use my little formula with the kappas and all that, and I see that this is just kappa left inverse and kappa right inverse. And compose with the omega left, omega right, that becomes an omega plus and omega minus. So this is the simple derivation. So what you see now is that you have an omega plus at temperature beta and an omega minus at temperature beta right, meaning the state, the stationary state, is the one where you have thermalized all the right movers with inverse temperature beta left, and thermalize out the left mover with inverse temperature beta right. And this is what we see here, right? T feels the beta left and T bar feels the beta right. That works for all for the full algebra, and so that describes the full state. Okay? So, any questions about this little derivation? So it's a very physics-based derivation. Then, okay, simply evaluate the exact current, as I said there, so the exact formula. So, you know, in physics, when we find a formula, we have to check it. Well, in physics, we usually don't provide the complete proof, so there are two ways to check the formula, well, three ways actually. Either you do some numerics on the computer and check if it's right, either you do an experiment and check that it's right, or you do the proof or ask a mathematician to do the exact proof and check that it's right. Well, in this case, the three things have been done, happily. So, how are we going there? Numerical check, I'll come back to this. Numerical checks is being checked numerically, so people have put the Heisenberg chain on the computer, evolve it with time, go at very low temperature. The low temperature should be described by a CFT with center charge 1, and calculate the current. And okay, it's not trivial, right, to do that actually numerically. And they found exactly that. They found this pi over 12, the right number is the right difference of temperature. Okay? Now here is very interesting. So this is, of course, the calculation is numerical, so it cannot be in CFT, right? CFT is a field theory. It's got to be on a quantum chain, something you can put on a computer, right? And so this reminds us that when we do something in CFT, well, it's got to be connected to some quantum model if you want it to have a meaning, a bit more of a meaning. Okay? And how it's connected? Well, what they found is that it was true at low enough temperature. So the CFT result gives you the low temperature region of this quantum chain result. So if you were to calculate exactly this thing that I said at the beginning for the quantum chain, you should find this plus something of order beta to the minus cube. Okay? That's a prediction, and this CFT prediction that agrees. There's also an experiment that has checked this similar thing. This is an experiment with quantum dots, essentially. And there's also rigorous proof, as I said, recent rigorous proof by Hollands and Longo, where this stationary state, as described, was calculated exactly. In fact, was calculated for the extended algebra, not just the energy sector, but the full algebra of operators in rational conformal field theory. So this is all correct. Physical interpretation of this. So certainly the natural one is to say that the right movers and left movers are independently thermalized, as the picture shows. Okay? But there's another physical interpretation that connects with what I said at the beginning. At the beginning, I said, well, it should involve the energy and the momentum, right? That's from natural argument. Well, indeed, this is the case here too, because the H plus and H minus, which are involved in these KMS states, combine to give an H and P with various coefficients. So that calculates exactly the beta and nu that I had said in the beginning. Okay? So in CFT we have this. It can be interpreted as the boost of a thermal state with a certain rest frame temperature and certain boost velocity. Okay? So this has the two interpretations of independently thermalizing left and right, and of a boosted thing. Okay? Okay. Any questions about this CFT result? Okay. So that's the CFT result. We have a bit more also because of the very simple CFT evolution. In fact, what's happening is that the whole space-time profile can be understood, not just a stationary state. So as we evolve, there's a contact discontinuity. It's the hydrodynamic expression. On the left it's hot, on the right is cold, is the initial bath. In between is exactly the steady state with a sharp change of state. Meaning that if you were to evaluate average of anything in the energy sector, this is what you would observe. This sharpness, I believe, is becomes diffuse if you go beyond the energy sector. You correct me if it's right. Beyond the energy sector, if you go to rational safety, look at other fields, it's not sharp anymore. And I don't know exactly how to describe it as of yet. Okay? So we know how to describe the stationary state, but this whole thing is not completely known. Okay? That's an interesting problem as well. Okay, so that's the situation. I wanted this another little subject that goes beyond that, which I want to describe. But before, natural questions that can be asked is, what about going beyond conformal field theory, for sure? Okay? Well, in QFT, there should also be something. We have predictions from hydrodynamics. There's no exact calculation, but it should be possible, to calculate this beta in nu in principle, right? It should exist and should be possible. So we have predictions for these things, which are complicated integral equations or equations that one can solve numerically. Okay? And in free particle models, so XY chains, for instance. Okay, not the Heisenberg XY chain. Well, this has been solved and with mathematical precision using operator algebras, by the way. Okay? And in free particle models, what has been found is that the stationary state is a state where you thermalize left and right movers independently. That makes sense in free models because you have left and right movers. Okay? So you have two very different pictures. One of them in QFT, beyond CFT, it should be H and P. It should be kind of a boosted thermal. While in free particles should be independently thermalizing left and right. It's a very different thing in general. In CFT, it turns out it's the same. And in integral models, there's some kind of hybrid description that we have found recently. Again, it's from hydrodynamic idea. So here, there's a lot of open problems, let's say, a lot of interesting things to look at, proving that the stationary state has the form we expect, like boosted thermal or something else, and calculating exactly these values. Okay? Or proving even that the limit exists, now that. Okay, so that's interesting. Questions about that? Yes?
So you're saying that experimentally people can detect the effect, the relativistic effect on heat transfer like this?
So the relativistic effect, where it comes from, it's an emergent relativity. It's not the relativistic effect of the fundamental particles. Okay? So if you think of a system with electrons, that electrons have very low energy, they will fill in some bands and then stop filling them because they're fermions, and then you have a band, a Fermi energy, which is until which the band is filled. Okay, and if you look at small excitations above that, okay, so there's this usual picture where you have you fill the band like that. Here's how it feels. Small excitation above that. Okay. This is they will feel energy kind of up and down that are very near to the position where the band is filled. This is perhaps not very clear. So this is filled and energy up and down very near. Okay, and if it's very near, what they will think, these excitations, they will think that the band is linear. If the band is linear, that means that the energy is proportional to the momentum. And that's the relativistic dispersion relation. And so you have emerging relativity in low energy quantum system. This is very interesting.
Like we have Weyl equation in graphene.
Yes, because exactly. But so in graphene is something similar to that, for instance, but you can have a gap there. You can have actually massive QFT, relativistic QFT in graphene, in fact. So but it's something similar. So it's an emerging relativity. It's the excitations that fill this special relation. And it's not the speed of light. It's the speed associated to this Fermi energy. And that's what they see. Other questions? Okay, so the last bit I will just say, I will not give you the derivation but the result and just the idea. So we want to study a non-equilibrium system, actually a very important theory in the modern study of thermodynamics and non-equilibrium thermodynamics is called the large deviation theory. Okay? And we've done that also with Denis Bernard. We've studied the large deviation theory of non-equilibrium CFT. What is that? Well, this is a theory that describes not just the transfer of stuff, currents or particles or anything like that, but also their fluctuations. How does it fluctuate with time or because of quantum fluctuations or because of classical bath or something like that, the fluctuations. So the origin of the fluctuation depends on the system, depends on the physics of it, okay? But how the fluctuations behave is rather universal, okay? So it's a very beautiful theory that describes some universal results for all these things. And we wanted to check if in our CFT, these results that are supposed to be valid in our kind of situation indeed were valid. Okay, that's what we wanted to check. So calculate the appropriate functions within this large deviation theory and check that it satisfies the right appropriate equation. Okay. So the idea, maybe this is too many words, but the idea is relatively simple. So we think, so what we want to calculate is the following. We think we have this system with left and right, different temperature. And we first, so we make a two measurement protocol. So we make a measurement of energy at the initial time. Well, the system, of course, gives thermals to the fluctuations which are classical in quantum, but you make a measurement. Okay, that's a projection operator here. Von Neumann measurement. So what you make a measurement is the difference of energy between right and left. Divide by 2. Measure that. You get a number. Now, that changes the density matrix, of course, so it gives you a number. Now you let the whole thing evolve for a very large time. It's large deviation, you let the whole thing evolve for a very large time. After a large time, you make the measurement of the same thing again. So there's a large amount of energy that will have flowed from one side to the other. You get a different number, ET, okay? And also a different density matrix. And then you want to evaluate the joint probability of these two values, probability. So it can be calculated in quantum mechanics. Okay? It's traced with projectors, with initial density matrix, and all that. Okay? Joint probability. And what you want to look at is the scale cumulant generating function for this difference of energy of measurement in the two von Neumann measurements. And that difference is nothing else but the energy that has been transferred from one side to the other. That's what it is, right? Energy transfer from one side to the other. And so you construct this generating function for the cumulants, which is that sum with the parameter lambda. It can be written in terms of quantum mechanical operators, okay, with a trace. Okay? And the scale cumulant generating function is the large time limit of this generating function for the cumulant scaled by certain powers of t. Okay? Which power? That will depend on the observable. You have to choose the one that makes it converge. Okay? And in our case, it's alpha equals 1. So it's a quantity that's scaled with t, but this you have to show, basically. Okay? And that thing, f of lambda, is the central object in the theory of, in the large deviation theory. So that's the central object. That describes the large scale fluctuations. Okay? So you see, you measure energy initially, and at the end, you take the difference. That's the quantity of energy that has been transferred. You look at the cumulant for this random variable, random variable. And these cumulants, they become very large, of course, as time increases because there's a large quantity of energy that has been transferred. You divide by t to get something finite, and you get a number, and that's the quantity that is part of this general theory. Okay? So the general theory tells you that the probability that the scaled random variable, energy transferred, takes an exponentially decaying form as t is very large, where the coefficient of this exponentially decaying form is something called the Legendre differential transform of that scale cumulant generating function. So f of lambda is important to describe this probability. F of lambda also satisfies something that is called a fluctuation relation, some kind of symmetry relation. So that depends on the betas. Okay? And this is the thing that is non-trivial actually. This kind of follows from general theory with certain assumptions. And one of the aim was to first calculate this f of lambda and check its fluctuation relation. It is very fundamental to that theory. It says that the probability that the current being transferred went in the correct side, from large temperature to low, divided by the wrong side, from low to large, this probability is exponentially decaying. That's what it says. It says that most likely it's going to be transferred in the right direction, but sometimes in the wrong direction with exponentially decaying probability. Okay? So the calculation of f of lambda in CFT and the verification of that formula. So this is rather non-trivial actually to calculate that, because you see all the formulas that I've given for f that make sense in quantum mechanics completely, but we want to take large T, large volume in all that, so we have to be very careful with that. Okay. So we've calculated it. I skip the derivation. I just go to the result. Okay. So the derivation is again based on physical arguments. Go to the result. We have an exact result for that. Okay. So it's simple formula. F of lambda is always convex, so it has this form. Sometimes it's infinity. So here it's infinity beyond a certain interval, from minus beta r to beta left. Outside of that interval, it's infinity. Okay. In that interval, you take that particular form with a coefficient c pi over 12, which is the same as for the current. If you take the first cumulant, this is just the average current, you come back to the formula we had in the beginning. But the higher cumulants, well, there are new formulas from conformal field theory, and it is a prediction for that. This formula we've checked afterwards then satisfies the fluctuation relation, this fluctuation relation, so the large deviation theory holds within CFT, which is actually not completely trivial. In fact, the quantity f of, okay, I'll come back here, f of lambda t for finite t is actually very ill-behaved in CFT. It has UV divergencies. It has a lot of divergency if you try to calculate that. So the colliding points, now that's where one has to regularize. So this is it's very messy. Okay? Contrary to the current, which was not rather messy. But if you take the large time limit, then all these divergencies disappear. That means that this large deviation theory is actually universal from the point of view of QFT even. Right? And this f of lambda also has a classical interpretation as Poisson processes, so you can look at CFT out of equilibrium as being a set of independent Poisson processes that carry energy from left to right with various probabilities determined by the Gibbs distribution. Okay? So it has a lot of nice interpretation, kind of semi-classical interpretation, and it is universal, satisfies fluctuation relations and all that. So this is a result. It was actually the first time that a scale cumulant generating function was evaluated in the quantum system beyond 3 fermions. It's a quite interesting result, but it has not been proven rigorously yet, and I believe it is fully treatable within the rigorous framework of conformal field theory. Any questions about that? So I think this is a very nice open problem. Okay. Yeah, so that's it. So I think that's mainly what I wanted to say. So some open problems, as I said, I mean, rigorous proofs of what we expect physically for QFT and for CFT in higher dimensions. Also, the exact calculation of stationary state in these cases. I should say that beyond CFT, the most powerful way to calculate the stationary state is using a theory of hydrodynamics. It's a completely different set of assumptions now that. And I think a very interesting question is to understand more rigorously how hydrodynamics emerges in a quantum system in states which are inhomogeneous. This is very interesting questions in the context of non-equilibrium system. Okay? And well, so understanding this scale cumulant generating function also in CFT, that should be within the reach of current methods. Yeah. So thank you for your attention.
Thank you for this very interesting talk. Is there any question?
I just have I'm curious how you can get the formula. You can arrive at the formula, but you don't have a proof of it. I mean,
so yeah, I can go over the steps. So I derive it, and at every one of the steps, I make some assumptions which are unjustified. So that's That's how I don't
Okay.
have a proof. Okay.
But then,
But with physical intuition, that should behave that way. That should be okay. Okay.
making it rigorous, would mean justifying those assumptions?
That would be one way, or maybe there's another way of calculating it out.
Yeah.
Okay. But here you see the steps. The idea here maybe that would be a good way of reversing. So you first take a derivative with respect to lambda of that thing. You evaluate the derivative with respect to lambda. Okay.
Yeah.
That's simpler because when you take derivative with respect to lambda, you have something like that. So you have an integration where you have a big trace. Okay, you'll define all that. But in that trace, there's a local operator. And the trace with stuff on the top and bottom which are the same, and the local operator on the top, that kind of trace, you know how to deal with that in general. So I think that things rigorous that can be done there. Okay. So the first thing is that there's some h left plus h right, which you replace by h. So you put the little h left right in there by assuming that it doesn't make a big change because it's in the trace in top and bottom. So I don't know, but assuming that this is okay. So you can change your trace a little bit by something which is a bit simpler. Okay?
But these traces exist.
So these traces, this is supposed to be in CFT infinite volume. So no. So I don't know, right? It's already there. Okay, this is a formal notation. Okay, but one expects that, blah blah. Okay, so you expect that you can make this change there. Then you have that. So in that, since this is local, you expect that the main contribution is within a region of the integral when t is large, and the boundary of the integrals don't contribute too much. And so you can now replace that. So and there's a 1 over t somewhere I probably forgot. So yeah, exactly. You take the 1 over t because of scaling. So you replace that then by just a single operator at a single point. So again, what's happening at the boundary, we haven't specified that. Okay. So I think it's correct. Okay.
Does it agree with experiment?
So there's no experimental check of that. Now that I say that, there might be some checks of some of the cumulants, but we haven't checked that yet.
No.
So I don't know. So
Right.
this is everything's to be checked there, even the numerics as well. So this is completely quite open. And the last step is so taking then the large T limit within this trace by assuming again this can be assumed that things that are far don't contribute too much and etc. So you get to a formula which is again all these formulas are all formal, but the last formula which is formal can now be reinterpreted as a stationary state at a shifted temperature. And now this makes sense.
Yeah, sure. Yeah.
So you see this formula dd lambda f equals that. That's the thing that has rigorous sense.
Okay, yeah.
If you can have defined f rigorously, And so now with that we can calculate it. So all the steps are approximations which we haven't fully justified, but which seems to make sense. Other questions?
So in the context of topological phases of matter, I've heard physicists talk about quantization of heat conductivity when they have a formula for heat conductivity in terms of essential charge. Is that?
Yeah. So there.
Can you comment on that? I don't know exactly what question to ask, but is it the same thing as what you're doing, or is it different? I mean.
I think it's slightly different. So this is a slightly different thing. Yeah, there is a quantum of heat conductivity, but it's not exactly what we are describing. What we are describing is near criticality, the central charge involved, whereas in that case it's not quite the central charge of the CFT. It's a slightly different situation, but I cannot comment. I cannot give a very intelligent comment besides that on that. So I think so it's a bit different, I would say.
Make a comment that in fact I told you that the right way to take care of this boosted KMS state is consider this Buchholz relativistic KMS.
Yes.
So this I think is something that you don't see here because it's really infinite volume. That when you are in quantum field theory, the KMS condition gives some analytic continuation.
Yes.
But because of the relativistic invariant, we have analytic continuation in a larger region.
Yes. Yes. Okay.
That's I guess should play a role because it's intrinsically relativistic condition.
Yes. So I know you told me yes, and I don't know exactly how it would play a role in there. That's a good question.
If there is no further comment or question, we thank again Benjamin. once again at